Show reverse footage of an egg unbreaking, then state, the laws of physics say this is fine. An egg unbreaking. A shattered glass pulling itself back together. Smoke crawling back into a cigarette. The equations have no problem with any of it. Newton's laws, Maxwell's equations, the Schrödinger equation, all of them work perfectly forward and backward. Time is just a number. You can plug in plus t or minus t, the math doesn't care. But you have never once seen an egg unbreak. So what's going on? Why does time only move forward? Physics doesn't have a complete answer, but it does have three main suspects: thermodynamics, cosmology, quantum mechanics, and none of them fully did it. Let's interrogate them. Suspect number one, entropy, the thermodynamic arrow. You've heard this one. Things fall apart. Disorder increases. The universe gets messier. That's entropy. Entropy is a measure of how many microscopic arrangements look identical to you on the big scale. A clean room has low entropy. There are only a few ways for everything to be neatly stacked. A messy room has high entropy. There are millions of ways for stuff to be scattered everywhere. So if you just randomly shuffle things around, you will almost always end up with mess. The second law of thermodynamics says entropy tends to increase in an isolated system. That gives time a direction. The future is the direction where entropy is higher. Egg breaks, entropy goes up, egg unbreaking. Entropy would go down. That's why you don't see it. Seems solved. But here's the catch. Entropy itself has no arrow. Ari Ben-Naim published a paper in 2020 pointing out that none of the standard definitions of entropy contain an internal indicator of time direction. Not the thermodynamic version, not the statistical version, not the information theory version. Entropy doesn't know which way is forward. It has no built-in direction. The second law is not a law like gravity. Gravity always pulls masses together. The second law does not force entropy up. It's just a statistical statement. If you have a million dice all showing 1 and you start shaking them, they will almost certainly become a random mess. But the dice don't have a built-in arrow. The shaking is symmetric. It's just that there are way more messy states than tidy ones. Entropy increase is overwhelmingly probable, not required. So the thermodynamic arrow is not a fundamental force. It's a statistical ghost. And that raises a much weirder question. If entropy just tends to increase, why was it ever low in the first place? If you walk into a room and see a million dice all showing 1, you don't think, well, that's just a random fluctuation. You think, somebody set this up. The universe started with all dice showing 1. That's the only reason entropy has been increasing ever since. That brings us to suspect number 2. Cosmology, the Big Bang. The early universe was smooth, hot, dense, almost perfectly uniform. That is an extremely low entropy state, especially for gravity. Smooth stuff has low gravitational entropy. Clumpy stuff, galaxies, stars, planets, has high gravitational entropy. Over billions of years, gravity pulled matter together. Clumps formed. Entropy shot up. That's the cosmological arrow. The expansion and clumping of the universe gives time a global direction. Sean Carroll explains it clearly. The only thing that makes the past different from the future is that the universe started in an anomalously low entropy state. The past is the direction where entropy was lower. The future is the direction where entropy will be higher. That's it. But why? Why did the universe start that way? Why was the Big Bang a million dice all showing 1? Nobody knows. It's called the past hypothesis. The postulate that the early universe was in a special, wildly improbable state. And that hypothesis is just a fancy way of saying, it was like that, and we don't know why. Roger Penrose pointed out that the initial low entropy is staggeringly precise. The odds of it happening by chance are basically 0, a number with more digits than atoms in the universe. So the cosmological arrow is real, but it's just a historical fact, not an explanation. The universe started weird. Now it's less weird. Time points from weird to less weird. But the weirdness itself is a complete mystery. Fine, maybe quantum mechanics saves us. Suspect number 3, the quantum arrow, wave function collapse. In quantum mechanics, particles exist in superpositions, multiple states at once. An electron is here and there. A cat is alive and dead. The Schrödinger equation describes how these superpositions evolve, and that equation is perfectly time-symmetric. Run it forward, run it backward, it works the same. But when you measure the system, something happens. The superposition seems to collapse into one definite state. The electron is here. The cat is alive. That collapse looks irreversible. It creates an arrow. Before measurement, fuzzy cloud of possibilities. After measurement, one sharp reality. So is measurement the source of time's arrow? Probably not. The problem is that collapse is not in the Schrödinger equation. It's an extra postulate. And physicists have been arguing about it for a century. In the Copenhagen interpretation, collapse is real but mysterious. In the many worlds interpretation, there is no collapse. The superposition just keeps going. The universe splits. Every possibility happens. Time symmetry is preserved globally. In decoherence-based approaches, measurement irreversibility comes from entanglement with the environment. The quantum system leaks information into a zillion surrounding particles. That looks like collapse, but it's really just entropy increasing again, which means the quantum arrow might just be the thermodynamic arrow in disguise. You still need a low-entropy pass to make decoherence push one way. Without that, the arrow doesn't emerge. So quantum mechanics doesn't give you a fundamental arrow either. It either has no collapse, or the collapse depends on the same initial condition problem we already had. 3 suspects. None of them guilty in the way we need. The thermodynamic arrow is just statistics. It describes the direction, but doesn't force it. And it only works because the past was weird. The cosmological arrow is just the fact of that weird past. It names the initial condition. It doesn't explain it. The quantum arrow is either an illusion, or it secretly relies on the other two. So where does that leave us? Time moves forward because the universe was born in a state of ridiculous order, and it has been relaxing ever since. That's the working answer. But the deep why is wide open. Why was the early universe so smooth? Why did it start with such low entropy? Was it inflation? A multiverse selection effect? Some deeper law we haven't found? We don't know. The arrow of time is not a fundamental law of physics. It is a historical accident, a fingerprint of the Big Bang, a clue we still can't read. Every time you watch an egg break, you are watching a message from the birth of the cosmos. And nobody has decoded it yet.